Page 826, section 12.3, we're looking at what the book calls the tangent line problem. And basically the idea is I want to find the slope of a tangent line at any point along a graph. On 826 it says calculus is a branch of mathematics that studies rates of change of functions. If you go on to take a course in calculus, you'll learn that rates of change have many applications in real life. So earlier in the year, we studied slope. But every time we studied slope, we looked at slope of a line. Now, if you calculate the slope of a line, it is going to be constant at every single place on that line. That would not be true for a curve, though. For instance, if you look at this parabola that we have here that would represent a quadratic, if I'm trying to find the slope of a tangent line at this point, that slope looks pretty steep. It looks like it might be like a +4 or something like that. Whereas if I come on up here and I look at the slope of a tangent line drawn at this point, that's going to be more like a +2. This is going to be 0. Over here, these are going to be negative. So you can see that if it's not a line and you're not working with a linear equation, your slope is going to change depending on your position on that curve. So they tell me then that in the middle of page 826, to determine the rate at which a graph rises or falls at a single point, you can find the slope of the tangent line at that point. In simple terms, the tangent line to a graph of a function at a point is the line that best approximates the slope of the graph at that point. Now, something else about tangent lines that we want to make sure that we understand. In geometry, we typically drew a tangent line to a circle, and so its definition was a line that touches a circle in exactly one point. And yeah, when I'm drawing a tangent line to a curve, I do want it to touch at only one point. But there are times that as that tangent line extends, it's going to cross that graph again because this is not a circle. And that's perfectly okay. This is still considered a point of tangency because my line is touching my curve in exactly one spot, even though maybe extended on out it would touch it somewhere else. So over on the top of page 827, it says, because a tangent line approximates the slope of the graph at a point, the problem of finding the slope of a graph at a point becomes one of finding the slope of the tangent line at that point. So in example 1, when it says use the graph in the figure to approximate the slope of the graph f of x equals x squared at the point 1, 1, as they just told me, the problem of finding the slope of a graph at a point becomes one of finding the slope of the tangent line drawn at that point. So I'm going to come over here to 1, 1, and I'm going to hand draw a tangent line to the best of my ability. It's not going to be perfect. But I'm going to try and draw a line so that it only touches that curve at one point, and the one point where it touches is at 1, 1. Okay? Then I can calculate the slope of that line. Now, you could do that a couple of different ways. You could literally count your rise over run. So I could identify a couple of points on that line that I drew, and I could say, okay, to get from this point to this point, I rose 2 and ran 1. Rise 2, run 1. So I could say, okay, my slope then is 2 over 1. You could use slope formula. So you could identify any 2 points on that line, like I have the point 2, 3 and the point 1, 1, and then I could just do y2 minus y1 over x2 minus x1. That would also give me my slope. Now, there are numerous ways to do this on your calculator, but grab your graphing calculator and let me show you one of my favorite ways for doing this. We'll learn quite a few different ways of doing this next year. But go to y equals on your calculator, and let's put in this equation. All right, so our equation was y equals x squared. So we'll load that into y equals. If you'll notice right above program, you have a draw button. So I'm going to go to second program, which will give me my draw menu. And I'm going to come down here to option number 5, tangent. Let me reset my window because my window's doing funky things. All right, so I'm going to go back to a zoom standard. Go to draw and tell it to draw a tangent line. Now that I'm on a normal window, it'll be easier to see. Now, you can tell it any value that you want to, right? So if you remember just a minute ago, we were drawing the tangent line at 1, right? So I can come over, and as soon as I start typing, it'll take whatever value I give it. So if I need to give it something precise like 1.476, I could do that. So I'm going to tell it x equals 1, and when I do, it draws that tangent line that we just hand drew a second ago, and it also gives us the equation of that tangent line. Now, we just calculated the slope of that tangent a second ago, right? And when we calculated our slope, we got 2. So if you think about it, this is y equals mx plus b. So that would be a slope of 2. So I can get my calculator to do this more precisely than I was doing it by hand a moment ago, just to verify that I was coming up with the right value. All right, so overall on page 828, they talk to us about the slope and limit process. If I want to calculate the slope of a tangent line, I need 2 points, right? y2 minus y1, x2 minus x1. But by definition, a tangent line is only going to touch a graph in 1 point. So I need a way to approximate the slope of that tangent line because I only have 1 point and I need 2. And so what they suggest to me is that I use a secant line. Because remember, a secant line is going to cross a graph in 2 spots, right? So they suggest to me, let's say that we've got this curve, and I want to calculate the slope of the tangent line at the point x f of x. They suggest, since I only have 1 point, x f of x, to draw a secant line that would use that point and would use another point on the graph. And so I could calculate the slope of that secant line, and that would give me an approximation for the slope of my tangent line. Now, I don't know about you, but I look at that and I'm like, yeah, but the slope of that line would be a terrible approximation for the slope of that line. Like, this one looks like it might be about 1/2, and this one looks like it might be a +2 or something. Why is that approximation so terrible? What would make it better? How could I make the secant line slope a better approximation of the tangent line slope? To what?
Is it 2 1/2?
What if I had those 2 points closer together? Like if we look at this drawing, I'm still drawing a secant line. I'm still going through 2 points. One of them is still x f of x, but look how much better of an approximation that secant line is to my tangent line because those points are closer together. So if I could get the distance between those 2 points to get smaller and smaller and smaller and smaller until it was just about indistinguishable. I do need them to be 2 separate points, but if they were so close together that you could scarcely distinguish the distance between them, then that secant line would be a nearly perfect approximation. The slope of the secant line would be a nearly perfect approximation for the slope of the tangent line. That concept sounds kind of familiar, right? Something getting smaller and smaller and smaller, closer and closer and closer. That's our idea of limit. So here's what we could say. We could say if the distance between these 2 points is approaching 0, so that they're so close together they're almost indistinguishable, then the slope of the secant line would be the same as the slope of the tangent line. And that is exactly the definition that we get for the slope of the tangent line. It is the limit as h approaches 0 of the slope of the secant line. Okay, how do we find the slope of the secant line? Well, come back over here and let's look at our 2 points. The first point we had was x f of x. We're going to say that the distance between the first point and the second point, we're going to say that distance is h. We do that a lot where we do x minus h, where h is the value subtracted from x. It's the horizontal shift. Kind of the same idea here where we're saying start at this first point and come over an h value to our second point. So if we wanted to find an ordered pair here, we could say it was our first x value plus the distance we moved over h. And then anytime you want to find y, you just take the x value and plug it into the function, so y would be f of x plus h. And it's the exact same thing over here when the 2 points are closer together. So if I want to find the slope, I would do y2 minus y1. So I would say, okay, f of x plus h minus f of x. And then I would do x2 minus x1. So that would be x plus h minus x. And so that would just leave h in the denominator. Now, this should look very familiar, right? Because that's exactly what we were doing in 12.2 when we were doing reviewing the difference quotient that we've seen repeatedly this year. This is a difference quotient, and in 12.2 we put the limit with it, and we said that that would be our definition of derivative. And so later on in this section, they do tell us that slope of the tangent line and derivative are the same thing. So let's look at example 3. Example 3, they give me f of x is equal to x squared at the point negative 2, 4. And they say find the slope of the at the point negative 2, 4. Same thing as finding the slope of the tangent line at the point negative 2, 4. So if I want to find the slope of the tangent line, I'm going to do the limit of the slope of the secant line. So I'm going to do the limit of f of x plus h minus f of x divided by h. Most of us would rather work with numbers than letters any day. So if x is negative 2, let's go ahead and put negative 2 in the place of x, negative 2 in the place of x. So if I have f of negative 2 plus h, that means put negative 2 plus h in the place of x in this function. So that would be negative 2 plus h squared. So negative 2 plus h squared. All right, then we'll subtract f of x, and that negative 2 in for x. So if we put negative 2 in for x, that would be negative 2 the quantity squared. And then the pattern says divide everything by h. So now we're back to difference quotients. We can go through and say if I have negative 2 plus h and I square it, negative 2 squared is positive 4. Negative 2 times h and h times negative 2 gives us negative 4h. And then h times h gives us h squared. Then we're going to subtract the negative 2 squared. So negative 2 squared is positive 4. We'll subtract 4. So our 4 and our negative 4 will drop each other out. And that leaves me with every single piece that has a factor of h in the numerator. So I'm going to go ahead and factor that out of the numerator because as it was, my limit was not well behaved because of the h in the denominator. I would get 0 in the denominator. So if I take out that common factor of h, I can cancel it top and bottom, and what I'm left with is the limit of a polynomial. Polynomials are well behaved. So I can just do direct substitution, and I'll get negative 4. So what we're saying is the slope of the tangent line at the point negative 2, 4, that slope is negative 4. Well, let's come up here and see. If I come up here to negative 2, positive 4, and I hand draw a tangent line, is it possible that that slope could be negative 4? Well, if I start right here and I rise a negative 4 and run a positive 1, absolutely that looks like I could fit that tangent line. I could go back to my calculator and check it on my calculator and see what my calculator says. So again, I've got my equation in x squared, and I'm going to hit graph to get my parabola. I do need to hit graph first. And then I'm going to go to second program, which is my draw menu, and choose option number 5, tangent. And it'll go back to my parabola. And remember, as soon as you start typing whatever number you want, it'll take it. So I'm going to start typing negative 2 and hit enter, and it will hand draw that tangent line. Well, not hand draw. The calculator will draw that tangent line for me. And then it will give me the equation of that tangent line. And so since that's y equals mx plus b, I can see m is negative 4. So that's the same thing that we just got algebraically, the same thing we got on our graph, and we've backed it up with the graph on our calculator. All right, look at another one. Example 5, we've got f of x is equal to x squared plus 1, and it says what's the slope at negative 1, 2, 2, 5, 1, 2, and 3, 10. Are you kidding me? This work that I did right here, you want me to do 4 times in one problem? Well, let me make a suggestion to you. If they ask you to evaluate a slope at 1 point, yes, go ahead and take that one value for x and plug it into your equation and work with it. However, if you're in a scenario where we are here, where they're asking you to evaluate it at multiple points, do not put a value in for x. Just leave x in there. Instead of getting a number at the end, you'll get an equation at the end that then you could plug in as many x values as you needed to. All right, let me show you what I'm talking about. Here's that same definition for slope that we've been working with. So I'm going to start off, if my function is x squared plus 1, f of x plus h means put x plus h in the place of x, so that would be x plus h squared plus 1. So x plus h squared plus 1. Then I'm going to subtract from that f of x. So f of x was x squared plus 1, so I'm going to subtract x squared plus 1. And I'm going to divide that whole thing by h. All right, so let's do some simplifying. X plus h squared, if I FOIL that out, x times x is x squared. X times h and h times x is going to give us 2xh. And then h times h squared, and then the plus 1. So this whole thing right here just came from f of x plus h. Now I need to subtract x squared plus 1. So when I do, of course, that's going to change both of my signs. It's going to be negative x squared and negative 1. Whole thing divided by h. So let's cancel what we can. The x squareds will drop out, and the 1s will drop out. And everything that I'm left with in the numerator will have a common factor of h so that I can take it out to cancel it top and bottom. What I'm left with will be a polynomial that I can use direct substitution to evaluate. But here's the thing. When I get my answer, this time it's not a number, right? Because I didn't replace x with a number to find the slope at one specific point, what it did was gave me an equation that I can use to find the slope at multiple points. So now I can go through and say, okay, if I want to find the slope at negative 1, 2, then if my slope is 2x and x is negative 1, then my slope is just going to be 2 times negative 1. It's going to be negative 2. If I want to find the slope at 2, 5, the equation for slope is 2 times x. The x value in that ordered pair is 2, so 2 times 2 is 4. If I want to find the slope at 1, 2, since the equation is 2x, I'm going to do 2 times 1. If I want to find the slope at 3, 10, since my equation is 2x, I can do 2 times 3, and my slope is 6. So then finding the slope at multiple points is much simpler. All right. So once we've got a firm grasp on the slope of the tangent line, they tell me over on page 831, hey, that thing you've been doing, the slope of the tangent line thing, yeah, that's a derivative. And we're going to have a lot of different notation for derivative next year, so I just wrote several of those notations here for you. So example 7, it says f of x is equal to the square root of x. Find this. Well, that's just one of the notations for derivative. That's all they're asking me to find. So I'm going to do the exact same thing that I've been doing all day, just a different name for the same thing. Because they're asking me to evaluate it at 2 different points, I'm going to leave x in there. So I'm going to say, okay, f of x plus h, put x plus h in the place of x, so that would be the square root of x plus h. And then subtract my original function, so my original function was square root of x, and then divide that by h. Not well behaved, so I'm going to have to do some algebraic manipulation. So we learned yesterday that if you had a radical, you could multiply by its conjugate to rationalize it, right? Whether it's in the numerator or denominator, in this case numerator. So I'm going to go through and multiply by the exact same numbers, but the opposite signs. That's its conjugate. So square root of x plus h times square root of x plus h gives me x plus h. Square root of x plus h times positive square root of x, and square root of x plus h times negative square root of x drop out. Negative square root of x times positive square root of x gives me a negative x. Just keeping the denominator the same. So my x's will drop each other out, and then the h will cancel in the numerator and denominator, leaving me a well-behaved function that I can use direct substitution. Now, when I plug 0 in for h, I'm going to get 1 over the square root of x plus the square root of x, so that's 1 over 2 square roots of x. Again, that's an equation then that I can use to evaluate the slope at the different points. So at 1, 1, I can put 1 in for x, and I get 1/2. At 4, 2, I can put 4 in for x, and I get 1/4. So here's our homework for section 12.3.